You have to memorize the formula for integration by parts. And basically what's happening is we're saying that if we have some ugly integral, if I have some ugly integral over here that I'm not sure what to do with, integration by parts lets me swap that integral out for hopefully a nicer integral. I don't want to redo any of the examples that Dr. Dedell did in class today, so I'm going to make up some other ones. So let's say that I was asked to integrate x cubed times natural log of x dx. So far, the only thing we really talked about is u substitution, and that's still going to be the first thing I'm looking for in a problem. So when I walk up to this problem, I'm thinking to myself, is it just algebra? Is it trig? Or is it a mixture of stuff? This is a mixture of things. It's a mixture of algebra and logarithms. If it's a mixture problem, I'm going to try u substitution first. And what I mean by try it, I mean I'm going to think about what's the derivative of x cubed? 2x. Sorry, 3x squared. Does that show up somewhere else in the problem? No. I'm going to move on to look at the natural log. What's the derivative of ln of x? 1 over x. Does that show up somewhere in the problem? No. So if it's not a u substitution, I'm going to try integration by parts. Dr. Dedell gave a great handy tip for trying to decide which part we're going to let equal to u and which part we're going to make dv. So to recap that, the acronym we're going to use is LATE. I think about LATE really as saying who sucks the most to integrate. Logs suck the most to integrate, so that's what I want to make u in any situation that I have. So that L stands for, we've got logs, algebra, trig, and exponentials. So when I look at my problem here, x cubed ln of x cubed is what we're going to classify as algebra. And algebra is anything that looks like a number times x raised to a power. Ln of x well, that's obviously a log. The way that I'm going to select my u to do integration by parts is whoever comes first in the word late. L comes first in the word late, which means when I do my u substitution, when I do my integration by parts, u will be ln of x, and everything else in the problem is dv. In order to use this integration by parts formula, which I memorize as ultraviolet voodoo, in order to use that integration by parts, I have a u and I have a dv, but now I need, for the formula, v and du. So I'm going to take a derivative of u, and I'm going to take the antiderivative of dv to get v back. I'm going to add 1 to that exponent and divide by the new exponent. So what this formula says is I'm going to replace this integral with u times v minus hopefully a nicer integral. U times v minus the integral of v du. Okay. In general, when I'm doing integration by parts, each time I've written a step, I want to take a minute to simplify before I try to do any integration. So here, it doesn't matter which order these are written in. By convention, if we have something, we put it in front of the natural log. I don't know why, that's just what mathematicians do. And here, I'm going to take that 1/4 and move it in front of my integral. And then inside of the integral, I've got x to the 4th over x, so one of those x's will cancel. And leave me with x cubed dx. Finding the antiderivative of this. And that's my final answer. In general, with integration by parts, you actually secretly end up integrating twice each time, because once you've identified the u and the dv, you're always taking an antiderivative to get from dv back to v. So this is sort of like a mini integral, which then hopefully when you rewrite this, gives you an integral that's easier to work with. Questions about this one before I do another example? Yeah, so the question is about the acronym, and logs, algebra, trig, and exponentials represent most of the types of functions that we're going to end up integrating. However, it is possible that we would encounter some inverse trig functions. This one's a little bit tricky for me in the context of the 17 series, because this is the first year that we've used this new textbook for Math 17. And in this textbook, the only inverse trig function that we take derivatives of is inverse tangent. So my guess is that we actually won't encounter a lot of inverse trig when we're taking, we might encounter inverse trig in the sense that the antiderivative of 1/1 plus x squared is tan inverse, but I'm not sure how much we're going to see inverse trig directly in an integral. But we can squeeze an I either in front or after the logs. For inverse trig. And if you all have friends that are taking the 21 series, they definitely need to know that. In the 17 series, in this textbook, I just don't think we're going to encounter it a whole lot. Maybe on some of Dedell's tricky discussion sheet problems. Other questions on this? Okay, I'm going to do a couple more examples. So here I've got a somewhat straightforward looking trig function. I'm looking at secant cubed x and trying to find the antiderivative. So for secant cubed, that isn't anybody's derivative. And if I were to try to think about a u substitution, the derivative of secant of x is secant of x times tangent of x. And I don't have a tangent in there. So a u substitution isn't going to help. So my only other option at this point is to think about integration by parts. But right now, it isn't exactly two parts that I can work with. So I'm going to take a step and rewrite this as secant squared x times secant x dx. Now, the acronym of LATE or LIATE is kind of going to fail us right now because we have trig and more trig. So the other thing that we want to think about in terms of selecting the u and the dv, u is the thing we're going to take the derivative of, and dv is something we have to take the antiderivative of. So looking at this, secant squared is somebody's derivative, so that's the part that I want to use to find my antiderivative. So I would let u be equal to secant of x, which would make dv secant squared x dx. As I mentioned before, to get from dv back to v, we're basically doing a mini integration problem. And then if I have u and I need to get du, I'm taking the derivative of secant of x. Putting all of that together back into our uv minus the integral of v du formula, we've got secant cubed x dx is equal to u times v, secant of x tangent of x, minus the integral of v du. So secant of x tangent of x, when I multiply those together, I'll have a tangent squared. And then I'm going to look at that and go, well, I wonder if there's a u substitution I could do. Derivative of secant is secant times tangent. Now I don't have another secant. Derivative of tangent is secant squared. I don't have another secant there to make a secant squared. So we might think about integration by parts again, but if I look at that, neither one of those is a convenient antiderivative. So instead, because it's trig, I'm going to turn to a trig identity. And the trig identity I need is going to involve tangent squared. I will squeeze it in over here. I did post in Canvas some trig identities that I think you definitely need to memorize for Dr. Jadell's class. And this is actually one that he mentioned last week, but cosine squared x plus sine squared x equals 1. Sometimes that's called our fundamental trig identity. That one you definitely should have memorized. And if we take all of the terms up there and divide by cosine squared, it's going to give us the trig identity we need right now. Sine over cosine is tangent. Cosine over cosine, well, that's equal to 1. And 1 over cosine is secant. And now, if I rearrange this, I can trade that tangent squared x for secant squared x minus 1. Now at first that doesn't look a whole lot better than what we started with, but I'm going to distribute that secant of x into the other parts and apparently get shorter. One of the things that I can do now, because I have subtraction inside of that integral, can actually break that apart into two separate pieces. And really one of the reasons that I wanted to show you this integral is that something happened in it that happened in the very last example that Dedell did in class today, that e to the 3x sine 5x. After doing integration by parts twice, we end up with part of this being identical to what we started with, which means that I can actually add this, the entire integral, to the other side of this equal sign, so that we're looking at twice the integral of secant cubed x dx is equal to secant of x tangent x minus the integral of secant x dx. And I know we're still not quite done with this because we still have to attack that secant of x. I'm actually going to flip my board around because I need a little bit more space to write. Okay. I'm just getting caught up with what I had on the other side. So I had 2 times the integral of secant cubed x dx equal to okay. More fun with trig. So if I'm going to take the integral of secant of x dx, my advice, honestly, is to just memorize what the answer for this antiderivative is. And those antiderivatives are listed in one of the appendices for the antiderivatives of all of the trig functions. But I can show you how we derive the answer for this integral. Some very clever mathematician a long time ago stared at secant of x and said, hey, I've got it. I know how we can integrate it. We just have to multiply by 1. Cleverly. And that clever multiplication by 1 looks like this. So we're going to multiply the top and the bottom by secant of x plus tangent of x. I don't want you to worry about how would you know to do that. Every time you see a secant of x by itself, this is the way that we're going to integrate it, which is why I also think it's worth just memorizing. The reason this works and is actually helpful, if I distribute the secant of x on top, then I'm going to end up with secant squared x plus secant of x tangent of x. And all of that is still over secant x plus tangent x. You might be thinking that that looks worse, not better than where we started. However, the derivative of secant of x is secant x tangent x, and the derivative of tangent of x is secant squared. So what that means is that entire integral really is du over u. And we know how to integrate du over u. That's going to turn into natural log of u, or natural log of absolute value of u. We are almost done with this entire integral, except for the fact that on that left-hand side, we're still looking at 2 times the integral of secant cubed x dx. To get the integral by itself, the integral that we wanted the value of, we're going to divide both sides by 2.